So here's the retina. You have a similar photograph in the textbook, and you should be able to say, which way is the light coming? Top to bottom, left to right, right to left, bottom to top. Which way is the light going? If the light comes from here and goes toward the back, if you find this colored section called the choroid coat, here's the choroid coat. These are the pigmented cells of the choroid coat. Light comes from here and goes through these Mueller's fibers or ganglionic cells, and these ganglionic cells. It goes through these sections called amacrine cells. What doesn't show is that this might also have blood vessels to the outside, or maybe blood vessels on this side. Keep on going and go through the nuclei of the cones and the rods, which are in this area right here. These are all the dense nuclei of the rods and cones. So for light to go through, it has to go through this layer of not photoreceptors, but bipolar cells, amacrine cells, nuclei of these cells, and finally hit something, maybe. If it does hit something, it sets off a depolarization, and that's the sense of vision. If it doesn't hit any cone or rod, then it goes through this pigmented area and is absorbed by the choroid coat in the back. Some kinds of organisms, if you recall, have biological mirrors. Instead of having dark sections like this, they have silver or kind of aluminum-looking kind of cones or cells situation in the back. And so what happens with those kinds of animals, the light goes through, the light goes through, the light goes through, goes through here, misses the cones and the rods, goes through the colored section, runs into the biological mirror, and bounces back out. So you get a second chance at seeing the photon. It turns out that that's some of the animals that you know about. You think sharks see very well? No. What do you think? They're actually excellent. Really? They have really good eyes because they have this thing that I just mentioned. It's called a tapetum. A tapetum. I'll put it on the board.
The reflector.
Yeah, it's a reflector.
Bless you. Thank you.
So sharks are one of the animals that has tapetum. So it turns out sharks see a lot better than you do in dusk and dawn. Not necessarily in light areas, you see just as well. At night, sharks don't see very well at night either. They see better than we do, but they're not great. But when there's just a little bit of light, their reflective choroid coat, or the reflective tapetum, allows them to see the light once or twice. A little bit more, it bounces around, you see it a second time. Know any other animals where if you put lights on their eyes, it looks like their eyes are lit up? Cats, bulls, some dogs, some breeds of dog, some cattle, sheep have about half of their retina. So there's some other animals. One of the animals that has a tapetum that's really good is the octopus. Again, similarly. Anyway, that's what the retina looks like. We see the nuances of about 3,000 different shades of color. We do that with a taste test as well. Here is one of the sensors that's in a capsule. Anybody remember what this is called? From anatomy? It has a bunch of layers or lamina.
Lamellated.
It's a lamellated corpuscle. What's the old name?
Ruffini? No.
But you're on the right track. Pacinian. Good job. It's a Pacinian or Pacinian corpuscles. What do they do? Pacinian corpuscles determine stretch, heat, pressure, pain, what? Pressure and vibration? Yeah. So you want to look through, if you read through the chapter, keep track of some of the sensors and what they do. Ruffinis are oriented laterally in the skin, they're for stretch. And a couple of other structures that we'll see are for pressure and vibration. A bunch of free nerve endings that go up into the epidermis do. Pain, yeah, as well as temperature. Here's a taste bud. It's just a diagram. You can see this part. Here are the secondary cells. Here are the taste bud cells themselves. And again, here we are with a bunch of cilia on the outside. Taste buds are on the papillae. They're not the bumps of your tongue. Those are way too big. These are the little bumps in the walls of your papillae. And we'll see that in a minute. When you burn your tongue, does it permanently damage your taste abilities, or does it grow back?
It goes back.
Yeah, it grows back. It's being worn out all the time. It's just that the intensity of burning your tongue with real hot coffee, something like that, just accentuates the problem. But you're wearing off these little buds, taste buds, all the time, just from the kinds of things. I mentioned it once before when we were still in the digestive tract. Aren't you impressed with this kinds of stuff your digestive tract, especially your mouth, can take? Everything from ice cold to super duper hot, really acid, really base, really sharp, kind of bland. I always think of habaneros when I'm talking about this. You know what they are?
Peppers.
Little peppers, habaneros.
Orange pepper.
Oh. One time in graduate school, I made some chimichangas, and someone said, well, use these. These little peppers are pretty strong. I said, yeah, but they're really little, so I used a lot of them. It's a mistake.
Oh.
Here's a model of the external ear. So is this a left ear or right ear?
Right.
Looks like a right, because here's the nubbin of the cochlea. Here are the semicircular canals. Here are the sections of the bones, the malleus, the incus, and the stapes right there. That's right, the malleus, incus, and the stapes right there. And here's the auditory canal or tube, and the atus. And here's the tympanic membrane. And again, they accentuate something on the order of 125 times. So could you hear a pin drop literally? No,
Yeah.
that's idiomatic phrase. Could you hear a pin
can.
drop if I dropped it up here?
Yeah.
Tell me now with a stupid vacuum. But ordinarily you could, especially if you were focused into it. And if you knew you really had to see how many times the pin bounced and you got it right, you get $1,000, what would you do? Move over to it so it's closer to accentuate it? Do one of these things? Do the external ears actually make a difference in what you can hear? You sure?
Yes.
Let's find out. When I say go, put your hands up like this and cup your ears. Not until I say go. And when I say stop, pull your hands away. A, B, C, D, go, E, F, G, H, I, stop, J, K. Think ears help?
Yeah,
Or
a little
external
bit.
ears just for glasses?
I don't
Oh,
think
they help
so.
a
They have a
lot.
purpose.
So if you have like really big ears, it might help.
Jumbo?
Pin those puppies this. Which reminds me, someone asked the last time we were talking about this, do animals with really big ears, like African elephants, for example, do they hear really well? It's a trick question.
I don't know.
Is it, do they hear really well anyway?
I think they hear well.
They hear really well, and they hear into infrasound. Elephants can hear at lower frequencies than you can. In fact, about the highest sound that an elephant makes is when it's trumpeting. Most of the sounds are guttural. For years and years, until about 1968, 69, something like that, if I picture that right, people that were mahouts, people that guided or controlled elephants, would put their hand up on the side and they felt gurgling and rumbling and stuff. And because elephants are vegetarians, of course, and they produce a lot of gas, you don't want to be around an elephant that has a gas problem. It's really bad, circus thing. But you put your hand on the side of an elephant, it feels like it's rumbling and grumbling. They always thought that it was digestive. It's not. Most of it is sounds that are sounds that elephants make in below what we perceive as human frequencies. They have infrasound, whereas bats and dolphins and things like that have ultrasound. That's a different deal. So, turns out, if you don't have big ears, you can still hear very well. But their big ears are usually used for temperature control rather than for hearing. Here's what we used to teach all the time. That is, bitter is at one spot, sour is to the side, salt is to the side closer to the tip of the tongue, sweet is near the tip of the tongue, and the various papillae were isolated. Filiform or kind of thread-like sections were in the middle of the tongue. The vallate or circumvallate papillae were near the base. And fungiform that looked like little mushrooms, they're in midway but off to the side. Where would I find some umami?
At the very back behind bitter, maybe?
Right in here somewhere?
Yeah.
Yeah. That's where the umami is. Savory taste. I know that part. Almost done. There's a Coke.
click in the view and preview.
Preview.
Yeah.
Well, there we go. It was right. So, where is most of the sweet taste undertone?
Tip.
Tip. Where is umami?
In the back.
Back.
Is there any other place where you taste? Or is it just on your tongue? Does your uvula taste food?
I don't know.
No. It's involved just in respiration. Skipping over. This is what some of you were looking at before. Here's olfactory epithelium. This is bone. And going through this bone are a bunch of holes. So if you recall from the skull anatomy, this is the cribriform plate with the crustagalli sticking up from it. And that little area, this is where the sensors are. So you could turn this upside down in your mind if you wanted to. But it does fold back and forth. Over the nasal conchae, these sections of the cilia are actually parts of sections that go back up to the olfactory nerve. Here's what it looks like in the epithelium diagram. There are basal cells, they're kind of like replacement stem cells. Then there are supporting cells like these, and the actual cells that are bipolar neurons actually have these little olfactory hairs sticking off. They have cilia, but they also have olfactory areas. What do you think of this kind of logic? Here's this section. This is a scent molecule of some sort. It won't latch onto any of these kinds of sensors that are on the cilia of the olfactory tissue until they match just right, like a lock and key. And that means that there are probably a limited number of smells that you can detect because you only have so many locks. There might be a lot more keys than there are locks. If you're sensitive to stuff blowing around in the fall, fungi, some kinds of things flower in the fall, like that, so you're allergic to things, usually you're allergic to a group of things because they all have similar keys to hit your lock. And when they lock up, they may be irritating in some way. So, about how many scents do you think we can detect? I mentioned it before.
2,000.
A couple thousand, yeah. Same deal. So, here we go. This is almost the last one I want to show you. Some kinds of animals, all species of cats, but a few other animals, have what are called vomeronasal organs, like right there. And in the vomer, that's part of the upper respiratory chamber, they have not only sensors in their nose, where the regular olfactory mucosa is, the olfactory membrane that we just looked at, they also have vomeronasal organs. They're especially isolated for some scents, particularly the scent of female cats. So a male tiger might give you one of these sniffy things, and then if he's triggered off, he might go and breathe. So there's a rapid flow of air across his vomeronasal epithelium because he's looking for a date, as it were. Lights are coming.